I got a couple of news links you might like here. This one I thought was interesting on the political point of view. This is a Florida Republican on tape, and they got the video here on Twitter of him telling people to make false registrations, pretend to have moved to Georgia, change their address so they can vote in Georgia, which apparently is a felony. And he totally told people to do it. He said he had done it himself. Then when confronted with it, he said, "Oh, I was just joking and I didn't do it." Then they looked up and he had really done it. He had falsified his home to move to Georgia to vote. And so then he lied about it again with another lie. And when they caught him on that, he changed it again. So this is actually a fourth or fifth case I've heard of this, of Republicans organizing voter fraud. So, you know, in a way, this is probably why Trump is so convinced that there's voter fraud, because the Republicans do in fact do it a lot. Anyway, so he got caught doing that. And this might actually matter. In this class, I don't know if you're bothering, previous times I taught it, we actually set up our own Ethereum server and such, and I sort of de-emphasized the cryptocurrency this time. But Ethereum has been talking for 10 years about switching to proof of stake instead of proof of work. And apparently they are going to do that. And they're also implementing sharding. And what these are is a way of moving the blockchain from the original Bitcoin blockchain back to basically a centralized currency. So it'll be much faster, have more transactions per second, and each transaction will not be processed by every node in the mining pool. That's what sharding is. You have a randomly selected group of like 100 miners verify each transaction instead of millions of people, so it is not so outrageously inefficient. And the proof of stake is the real part that is sort of the holy grail they've been trying to do for years, where instead of having to do proof of work, where all the machines are racing to find the hash value and only the one that wins gets a prize, so you waste a huge amount of electricity, there's going to be something where you prove that you have enough money invested. And the amount of money you have invested shows that you can be taken seriously and trusted. So really, it's all just moving back towards the original before the blockchain, where you had a company like Bank of America and you trusted them because they're rich. And that's what they've tried to do. And the proof of stake attempts in the past have been ineffective and easily hacked and such, but supposedly they're switching to it so that Ethereum will be able to handle more transactions. And they're really just moving it back towards a single centralized database. But anyway, we'll see where it goes. And blockchain is very bizarre. They claim it's going to do something awesome, but to make it work, they just have to turn it back into what it's supposedly rebelling against. It's very puzzling. So YouTube is going to introduce some feature to try to stop the comments. Everybody finds the comments on YouTube to be horrible. They certainly are. And so now they're going to, if you say something rude, they're going to detect it and then stop you and say you should keep your comments respectful, and then make you click a button saying, "I wish to say this rotten thing anyway." And they imagine this will stop people from saying so many rotten things. Lord only knows. But I know Facebook is the #1 company suffering from not filtering their social media. And YouTube comments are up with the rest, like Twitter. We're living through a time when all these things are going to be strongly pressured to stop having so much rotten content. But so far, nobody seems to have any idea at all how to block the rotten content or detect it, or even exactly what the rotten content would be. So anyway, we're here. This is 141. And this is the last lecture, quantum mechanics, quantum cryptography, which is, by the way, largely speculative and very impractical. And then the last class, I think I won't introduce any new material. I'll just be here to answer questions for that one, I think. So let me talk about this quantum stuff. The book has a good description, and I added some more to it. So let me get it here. And file, open recent. That should do it. Anyway, I don't think this is the right stuff. Nope. All right. Let me do it the other way. Which is here. 141. All right, there it is. There we go. All right, so we'll start with this stuff. I added quite a bit of stuff that's not in the book, but anyway, here's the point. And it's All right, so we're going to talk about how quantum computers work and what we can expect from them, and then post-quantum algorithms, which are really coming along. So in order to understand how quantum computers work, we need to go back to the very basics of how computers work in the first place. The normal kind of computer we're using is a digital computer, and it comes from these logic gates. So you have a NOT gate where you feed in input and out comes the output. If you feed in a 0, the output is 1. If you feed in a 1, the output is 0. Then you have an AND gate where you feed in two numbers, and if they're both 1, the output is 1, but if either one of them is 0, the output is 0. Then you have XOR that we've talked about a lot, that has a truth table that's half ones and half zeros. So if the two inputs are the same, the answer is 0. And if the two inputs are different, the answer is 1. And the whole point of digital computers is that they found a way to manufacture transistors that will do these operations on voltages simply and cheaply. So they could make chips that include millions of these components, and they could perform these operations really fast. And that's all digital computers do. It's just a series of these fundamental operations, flipping ones to zeros. And it turns out that that's all you need. But in the world, so if you want to make an adder, you combine a certain bunch of these things, and in comes A1 and A2 and B1 and B2, and this will combine in this group. It'll build it, and you can now build a series of transistors that will do anything you want, and that's what modern microprocessors are. Now, of course, you don't have any actual digital signals. What you really have are analog signals. The real voltages you have vary. There's noise and imperfections. So you take an analog signal in the real world, which varies between a high voltage and a low voltage, and then you take a region of voltage and call it 1, and another region of 0 and call it 0, a voltage, and then you have a forbidden region it should never be in. And you try to make it so that it will make a strong transition from being in the 1 zone down to the 0 zone, and spend as little time as possible in the forbidden zone where you don't know what's stored there. And you design circuits by having a high amplification of a signal followed by thresholding, so it jumps from one to the other and spends hopefully no significant time in certain states, because you really just want digits, 1 or 0. So that's what you do to create digital circuits. Now, that is a modern technique, digital computing, but we have had analog computing long before that. And here's one from thousands of years ago. They make a wheeled device that simulates the motion of the planets and the stars and the sun. So you could rotate a crank and these other things would move, and you could predict the location of astronomical bodies. These are just analog models of something built with gears and rotating bits. And those have been around for millennia. A slide rule is a similar thing. My father used to love his slide rule. He had one that was spiral and went 30 feet long. You could do like 4 or 5 decimal places on it. So you take the one number and you add it to another number, and you have a logarithmic scale. You can do multiplication and division, addition and subtraction here. And he's talking about driving a limo. Unless I add more finite rise and falling times, I get radio interference. Yes, that's right. So if you have these sudden transitions here in your analog signal, these create high frequency pulses. This, jumping a large distance in a short period of time, is a very high frequency. So it'll create a chirp that will hit a lot of other things. That's right. Anyway, so a slide rule is another form of analog computing. If you want to say how precise is this or how many bits does it have, it's not simple. I mean, it's a smooth scale. So the question is, how well can you measure it? How accurately is it built? You bring in like a magnifying glass to look more closely and read it. It's not entirely clear how many bits of data you have here. And somebody's got a Schmidt trigger link. Let's take a look at, yeah, this is a Schmidt trigger. Yeah, this is how you make a system that will jump from one state to the other. Yep, exactly. To take this kind of continuously varying signal and turn it into a digital signal. And of course, it's not a perfect process, and you create side effects like emitting these bursts of high frequency radiation as it goes. This is how you do it. So this is stuff that, you may not have even thought about if you're just using a modern computer to do computing. But let's see, it looks like my keyboard is, okay, good. All right, I should be able, there we go. Anyway, so you think of now, and believe me, this is really going somewhere. Then think about a flute. A flute is just a pipe And when you blow in one side with white noise and close certain valves, you create a cavity which causes certain noise to resonate and other noise to cancel out. So you get this smooth, continuous note. Your breath is white noise. You blow across a flute, which is a sharp edge. So you blow out really hard and you hit a sharp edge, which creates white noise. That's all it does. That's what's going on here. You're pursing your lips to blow hard and you're hitting a knife edge just to break up the air. This creates white noise, and the flute is designed so certain wavelengths are harmonically amplified as they reflect off the ends and other wavelengths cancel out, and that's how you get a note. And this is really important. This is the closest analog I could find to how quantum computers work. You create a mechanical object which will take input and turn it into the desired output. It does not follow a series of steps like a program where you do this and then that and then that. You just create an object which, when you put in the right input, will naturally cause the right output to come out. So, and it all works on these qubits. And qubits can be mathematically represented as a block sphere. So a qubit is what replaces a bit. Now you can have a certain state of 0 and a certain state of 1. That's at the top and the bottom. And if you just use those, you've got bits just like digital computing. But qubits also have these other values, which are in between 0 and 1. That's the magic of a qubit. A quantum bit can have an uncertain superposition state that is a mixture between 1 and 0. So in a digital computing, if you have a byte with 8 bits, there are only 256 possible bytes. So we talked about this last time. You got, I guess it was in the 126 class, you got Shannon entropy. That's the total amount of information you can store here is 8 bits of information in a byte. But if you have a qubit, 8 qubits, then you have the possibility of all of them being 0 or the last one being 1 or this one being 1, and you have a complex number with a real and imaginary part multiplied by these. So it's 256 complex numbers that are smoothly moving from 0 to 1. So this is enormously a much higher amount of information. You have basically taken 8 bits, and instead of that, you have 8 two-component floating point variables, vectors. So this is a much higher degree of information, and it's not even easy to say how much information it is, because how much information is there in a floating point variable? Well, it depends on how many digits of precision there are. So the actual amount of information available in a qubit depends on the noise level. How many of those bits are actually meaningful? And you could make a higher quality qubit, just like you could make a higher quality analog record player, and it would have more information and more precision. So why are the beta components, are they unreal? Yes, they are. These are all complex numbers. And that's why it's a sphere. You have 2 components. You have a real and an imaginary part. That's why you're on a sphere instead of just a circle. So it's in between 0 and 1, you have not just a linear mixture, but you have a whole 2-dimensional surface of a ball you can wander down. And that's, these are complex values. Anyway, so that's the point. So a digital computer, if you have n bits, you have n bits of information. If you have n qubits, then you have 2 to the n floating point values, which is a whole lot more information. And it's not as well defined. So now what you want to do is you feed in the input data with a state and a bunch of qubits, you run it through a circuit of quantum gates, and then you measure it, and you find an answer. And the goal of quantum computing is to figure out how to design these circuits to achieve what you want. But it is not like a process of having an algorithm where you do this step and get an answer, and then you do another processing step and get the next answer. It's much more like a flute. You put in the input, this circuit of things resonates and has signals bounce back and forth until it settles down like a gas cooling into a liquid, called quantum annealing is one of the techniques, into the final state, which is the goal you're looking for. So here's the quantum gates. This is the gate for measurement. Measurement has to be done at the end. Measurement causes the quantum uncertain states to collapse into either 0 or 1. After that, they no longer have any uncertainty. That's one of the magical things in quantum mechanics, which many people spend a lot of time struggling to understand, and they're actually making some progress with the latest physics experiments in understanding exactly how this works. But we've known for more than 100 years that is how it works. Quantum things like electrons are uncertain until you measure them, and then they become certain. They no longer have this mixture between 0 and 1. So you can only do this once at the end. Then you can rotate it about the x-axis. So a 0 would turn into a 1, and something that was half 1 and half 0 up here would turn into a different mixture of half 1 and half 0 down here, and so on. And you have a Hadamard gate. There's various ways to rotate things in this strange three-dimensional space, the block sphere. So now that you have taken these simple binary things like not and XOR, and you have replaced them by these weird things that do weird things to these quantum qubits. But it is the same general idea. You have some qubits, you have some operations you can do on them, and now you build a program by just combining these fundamental gates to build what you need. And it turns out that some problems get much easier to solve. And that's the quantum speedup. So if you think about searching a list of n items, if you're just looking for something down an unordered list, you just have to check every item to see if it's the one you want. And if it's there, you'll find it on average halfway down. So the expected number of operations is n/2 to find something in a list. In a quantum computer, you can find it in the square root of n operations, which is what it would be if it was, no, it should be the log of n if it was sorted. Anyway, it is the square root of n. There's Grover's algorithm that will do this. And here's another one. Simon's problem is essentially a hash collision problem. If you have a function, you're going to find two values that have the same hash value, and you want to find the relationship between those two values with this m. So you're going to find an m so that when you multiply one input by m, you get another which has the same hash value. It's not exactly the same as a hash collision, but it's closely related. That's called Simon's problem. And in a classic computer, that takes 2 to the n/2. We're familiar with this with hash problems. We talked about this. If you have an MD5 hash that's 128 bits long, you will have to calculate 2 to the 64 hashes before you'll find a collision because of the birthday paradox. But in a quantum computer, this only takes n operations. So it would only take 128 operations to solve that problem on a quantum computer. So certain problems get incredibly much faster. And here's a diagram of Simon's problem. You feed in all these entries and you have a quantum mess of gates and out come the answer. That's the way they all look at this level. It's just a block diagram. And then the one that really matters to us is Shor's algorithm. RSA depends on factoring numbers. You have this big number n, the public key, and if you could factor it into the prime factors, P and Q, you could find the private key and steal somebody's data that was encrypted with RSA. So the entire security of it depends on you not being able to solve that problem. And it turns out that the Shor's algorithm does, in fact, factor numbers extremely fast, and therefore would render all the current public key systems we've talked about, RSA, Diffie-Hellman, and elliptic curve, would all be shot. And Shor's algorithm, here's one example. This is the one that factors 7 times 13 into its prime numbers. And notice what it is. You just have a pattern of these gates, and then you measure it here. You feed in the information, and it just passes through these interactions and converges on the answer. And it's like the flute. You feed in the data, and the components in this of the vibrating signal that match the prime factors will be amplified by this series of connected things, and the others will cancel out. So what comes out is the prime factors. That's why it's not like you go through an algorithm where you divide by a number and compare it to something and then try the next number. It just goes through this object, which is designed to naturally converge to the right answer. All these things are proved conceptually. Yes, these are all theoretical. Mathematically, this is all that's all this stuff is entirely theoretical because there are no actual physical devices that can do this worth a damn. I think the largest number that has ever been actually factored on a real quantum computer is like 15, not even 15 bits, the literal number 15, factoring it into 3 and 5. That's the largest number we've actually been able to really factor with a real Shor's algorithm on a real quantum computer. So that's why you could argue that this is all complete nonsense. Quantum computers are in their infancy. The hardware is so weak, they can't do anything important yet. And yet we're all freaking out like they're going to destroy RSA. And the reason we are, of course, is because they're getting better fast. Nobody thinks quantum computers are going to be able to do anything that matters for maybe 20 or 30 years. But if you encrypt data today and store it somewhere, is it really okay that in 20 or 30 years somebody can decrypt it? And for a lot of data, no, but for some data like medical records and stuff, it's really not okay if that stuff becomes insecure in 20 or 30 years. So people are looking around the corner and trying to make better encryption that will survive the hypothesized improvements of quantum computers. So we can consider AES. AES 128, or familiar, if you want to do a brute force search to crack AES without the key, you have to try all 2 to the 128 possible keys. And just like searching through a list, you're likely to find it about halfway down. So it would be 2 to the 128 divided by 2. 2 to the 127 calculations is what it would take. And that's very secure because we've talked about this before. 2 to the 100 calculations is more than you can ever do on all the computers you can ever have. But Grover's algorithm does it in only 2 to the 64 calculations. You can cut this exponent in half, and that is entirely achievable. We cracked 56-bit key by brute force in 1997, and a 64-bit key, I think, around 2003 or so. So 2 to the 64 is an achievable number of calculations. So a working quantum computer would be able to crack AES 128 without the key. And here's what Grover's algorithm looks like. It's just another arrangement of these things, where you feed in the data and it converges. So this does a very small example of n equals 2 and a equals 11, whatever that is. But the point is, if you had, these are theoretical simulations, if you had a machine with low noise qubits and perfect gates that perfectly match the theoretical connections between these things, then you could do it. Anyway, so however, this is why we have AES 256. If you went to AES 256, then even Grover's algorithm would have to do 128, 2 to the 128 calculations. So that's why symmetric encryption is not really broken by quantum computers. All you have to do is double the size of the key, and your symmetric algorithms will remain completely secure as far as we know. So AES is fine. That's, you just go to the longer key value. But it is the public key algorithms that are in danger. All right. Now, like I say, this is all only theoretical because the hardware is not good enough. So if you, the problem is there's noise. Google and IBM make their qubits from superconducting circuits, little circuits that have superconducting magnetic fields as the current moves around. These things are cooled down to like milli-degrees above absolute zero, and they only remain stable for a few milliseconds. Another technique is to have ion traps where atoms are in special places and they tend to vibrate away. These are all the fundamental quantum objects, and all of them require expensive cooling, and they don't really stay in place very long. So they are noisy and unpredictable, and the connections between them, those gates, are also not perfect. They don't perfectly do the calculation they're supposed to do and nothing else. So in fact, it's not that good. And there's a bunch of people developing these things. These guys with individual atoms, they claim to have the most advanced quantum computer and so on. Everybody is jumping on board, building these things, just like everybody's jumping on board blockchain. But I think quantum computers are real and we'll get somewhere. And I think blockchain is nonsense and will not get anywhere. But I'm only guessing. Lord only knows what the future holds. So everybody's doing it. Here's University of South Wales claims they've done it. And there's IEEE Spectrum, another one. Shor's algorithm performed in a system less than half the size. They said it's less difficult. So the in 2016, the National Security Agency freaked out and they published a sort of emergency advisory telling everybody to begin moving to double the size of all their keys right away and to expect to have to upgrade all their encryption to quantum proof encryption. So in 2016, somehow, the American government, the military, freaked out about quantum computers. So one idea that a lot of us have is that means they have one working, a classified one. Nobody knows that. But somehow, apart from just, I mean, Shor's algorithm was invented in like 93, I think. It's been known for a long time, but nobody cared. But the NSA told us all we had to care just recently. And so that's what happened. So we'll talk more about this. The US government is telling us all these things are really coming. And in the past, when the NSA tells you something like that, what it means is they've got it. when it's classified. So we should be moving to post-quantum algorithms, which means you use a different kind of encryption that cannot be solved even by a quantum computer. So you need a different hard problem. All the ones we've done so far are based on the discrete logarithm problem. And so we have to have some other hard problems. So here they are: code-based, lattice-based, multivariate, and hash-based. Those are the four main types of other hard problems. So code-based are based on error correction. I remember this came out with CDs. When CDs came out for music, they said that these things will be the perfect music and you'll never need to buy another record or anything because they have digital storage and they have error correction. So if there's scratches in it or something, you can just totally reproduce the missing bits. In practice, it didn't work that well, but that was the plan. So here's one that can be used for encryption or signatures. Your key is 100 kilobytes in size, and it's based on error correcting code. So if you want to send a message over a noisy channel, you have to, if you want to send 3 bits, you have to send some extra bits. One way to do it is send every bit 3 times. If a single bit is wrong, the other 2 will outvote it. So this will survive a single bit error, but a 2-bit error can't fix it. So of course, real error correction is smarter than this. You send the message and then you send something like a hash, like a CRC32 sum every so many bits. So you send n bits and you encode it and send along another object, multiply it by matrix and send this along every now and then. That's the error correction bit, and that's how you do it. You have some degree of extra bits and redundancy that can be used to correct for errors. So McLeod's encryption. You have a secret combination of 3 matrices, and you have a random error bit, and that's encryption. You multiply it by A, B, and C are all private keys, and you can multiply them together to form G, and then you encrypt data by multiplying it and adding errors. So you have a big key and you add errors to it, just like you would, and people can decrypt it and remove the errors with the error correction process. And so the people who have the key can get the message, but it turns out that people trying to break it without the key have got a really hard problem that even a quantum computer can't solve. That's the idea. So this one is known to be NP complete. That's the idea. And then there's lattice-based. So if you have a lattice like this, just a regular pattern of dots created by going this vector and this vector, then there's a problem, which is find the closest point to here. And this turns out to be as difficult as the traveling salesman problem in general, the closest vector problem. If you have the 2 basis vectors and the lattice consists of all the points you can reach with integral multiples of these basis vectors, how do you find the one closest point? And that turns out to be very difficult. That's a hard problem. So now you can use this to form encryption. You make a random matrix and a prime number, and you're going to find a secret vector so that one is created by multiplying by the other on a modulus. So this is like elliptic curve cryptography. You're moving along this, you make a finite lattice and you're moving across the lattice. So anyway, here's learning with errors. Again, given A and B, find a secret vector. So this is true. It all look a lot like the discrete logarithm problem, where isn't traveling salesman essentially factorial? No, I think traveling, yes, I think that's a fair statement. I think the traveling salesman difficulty does go up with something like the factorial of n. That's right, which is very hard. Yeah, that sounds about right. And I think the same thing's true here. All of these are essentially that way. So I mean, they're hard the same way the other hard problems are hard, but in particular, they have shown that these cannot be solved on a quantum computer either, which I certainly do not know how they proved that, but that's the point. All right, and so they're all more or less equivalent, and they're believed to be hard for both classical and quantum computers. But the problem is, remember the video we saw a couple of classes ago about RSA? How RSA sounds good, but it turns out that very often when you pick prime numbers, you pick the wrong prime numbers, and RSA in fact becomes easy, and that really happened over and over. So there's the same problem here. These problems are hard, but there are parameters, and we really don't know which parameters are really good enough and which parameters are not good enough yet. So probably we're going to have all the difficulties that we had with RSA over again as we switch here. And so here's multivariate is another hard problem where you have 4 unknowns and 4 equations, but the equations are not linear. They involve multiplying them together, squaring them and multiplying, and that turns out to be quite difficult to solve in general. So that's another possible hard problem. Now, of course, again, it just depends on how hard the parameters are. For example, if it was linear and you didn't have any of these multiplicative terms, it would be trivial to solve. And I'm sure there are other parameters that make it easy. So again, it could be a hard problem, but there will be certain requirements on choosing your parameters to really use it for encryption. So this is not used yet, but it would create shorter signatures. And all right, then there are hash-based ones. Now, we already know that hashes are pretty good. And we also know that quantum computers cannot really break hashes very fast. So if you could make a scheme based on hashing, it would seem to be a good solution. And there is this thing called a Winternets, one-time signature. So what you do is you have a private key and you form your signature by hashing it with M rounds. M is your message. So if your message is 251, you hash it 251 times, and that's your signature. And somebody who knows your message can reproduce that process and verify the signature. So that's your public key is hashing your key with some other number of rounds. And there is no way to take something that's been hashed 10 times and predict what it would be to hash it some other times in general. So that's why it's considered secure. It's just got some serious limitations. You can forge signatures because the public key is formed. You can reach some messages by just rehashing the public key. Like if the public key is 10 times hashed, then you can calculate 20 times hashed and 30 times hashed and 40 times hashed. So you have the existential forgery attack. I can now create hashes that will match some messages, but not every message. So that's not perfect. And also, it only works for really short messages. Now look at the ridiculous amount of computation I've wasted. If I want to send a message that's only 8 bits long, I have to do 256 hash operations, which is a lot of computing. So that's pretty brutal. And you can only use it once. If you use the same private key twice, then I can really reach a whole lot of messages to forge now that I have 2 examples of public keys based on them. So, you know, it's quite limited as a cryptographic scheme, but it is not solvable on a quantum computer for what it's worth. So there are other ways to do it by adding more tricks to this multiple hashing process. And Sphinx is one of these schemes. And I think we're going to see that Sphinx is in fact one that is currently chosen. We're about to get up to the real choices. Anyway, so here's things that can go wrong with these mind-bending post-quantum algorithms. We don't know how secure they are at all because they're new. We're guessing what the parameters will be, and you really don't know in practice which parameters are going to be right. We already saw this with RSA. You do what looks right, and it often turns out that it's more difficult to choose good parameters than you think it will be. We might be too late already. There's already a lot of encrypted stuff. We're not going to be able to reach everybody. You know, the problem is people store encrypted data for years, decades, and of course, then it might be broken. So that's an issue. So it would be good when you do it to have layers of encryption involved to make it more difficult to crack. And of course, then there's the old implementation issues. You've got timing issues. And it turns out that the early quantum algorithms have had the usual kind of side channel attacks and so on. And so, of course, we know that the first generation of the new algorithms will probably make all the old mistakes. But here's the current state of report. IBM just announced, like last week with a press release, that they are going to sell quantum-proof encryption for your cloud storage on IBM Cloud. And I said, how can they do that? Because the algorithms aren't set yet. So I looked into it. This is the official US government status report on the post-quantum cryptography. In 2016, as I said, the NSA told NIST and everybody that we needed to develop these things. So NIST developed a public competition where people can submit things to, no, I can't give you a specific example of the side channel. I don't know. It's just in general terms. But yeah, we don't have any of these to play with much yet. But anyway, so in 2016, they started a competition, which is how they chose AES. And the current plan is that the standard will be chosen in 2022. They have finished round 1 and round 2. And one thing that surprised me, the second round candidate that I heard about that I thought was great was New Hope. This is Google's algorithm. Google invented one called the New Hope. I even found some Python code for it. I was even going to add it to the class, but I got distracted by other things before I could do it. And the thing that surprised me when I looked at this a few days ago is New Hope washed out. And by the way, the other one was Sphinx. Notice Sphinx is here. Here's Sphinx, that one that we were talking about based on hash values. It's one of the second round candidates. So they started with, I think, 46 of them. They boiled it down to like 26 in the second round. And then they had a third round. They just issued the selection about 6 months ago. And those are ones that are secure and fast and so on. And they wiped out New Hope entirely because they showed that New Hope is always inferior to Kyber. It's not any more secure than Kyber, and it's slower. So it's not even an alternate candidate. So these are the third round finalists, 4 for encryption and 3 for digital signatures. And these are the alternatives that were pretty good, but considered inferior to these. And they're now going to continue having people attack these and criticize them until sometime in 2022, when they will pick one and declare it the US government approved encryption scheme for post-quantum cryptography like AES. And it'll probably be one of these 4. And by the way, these crystals ones, I think, are the IBM ones. So Google washed out completely, and IBM is still in the running. And this might be why IBM felt so confident they've begun selling post-quantum cryptography even before it's approved by the government, because they seem to have great trust in their algorithm. And I must say, the same thing happened with AES. The things that made it to the last round are all perfectly fine. They survived enormous tests. They're just, one of them is going to be chosen as the official government approved one, but the runners up are also perfectly fine. So I guess I have to agree with the IBM marketing division that you might as well start selling this stuff. By the time you get this far, I think you can safely promise customers that their stuff is safe if I use my scheme on it. So anyway, that's where we are. And in a couple of years, we'll have official ones. And then I think it'll be the time to learn how to do it and start writing code and having projects with it. When it boils down to one, then we can all start learning how it really works. I don't think Cisco had an entry. I did not hear about a Cisco entry, but they might have. The only ones I heard, yeah, I thought Google would go further, but they didn't. Anyway, let's see if I can get this thing to work. All right. And I want to go to the Kahoot. I have one Kahoot for this stuff. All right, I'll give it a few more seconds. All right, what's a qubit that might be 0 or 1? All right, that's a superposition state. By the way, delete your Google machine. Some students tell me they're beginning to get charged by Google. So apparently this free trial thing has ended, and they don't get approval before they start charging you a few bucks on your credit card. So be warned. I guess our free ride on Google is over. Anyway, if you've been making Google Cloud machines, I don't know how many students in this class would have been doing that, but if you have, I would delete them. All right. All right, which one can break AES 128? All right, that was Grover's algorithm. Yeah. And which one is the closest vector problem? Yep, that's the lattice-based encryption. All right, a component that performs a computation on qubits. All right, that's a gate. All right, and which attack will break AES 256? Right, AES 256 is fine. Even quantum computers will not break it. All right, and which one does McLeish encryption use? That's the code-based, all right? I thought it was hash-based, but it's apparently the code-based one. All right. They'll have to tell me who they are. J.G. Dar may be a real name, but Heisenberg is probably not. All right. I see the name in the chat. Okay. The others look close enough to real names. All right. I'm going to stop the video and post that.